I'm here at Vasona Park in beautiful Los Gatos, California, not just because it's a nice day, not just because I need to get my dad outside, but because gentle hills like this one right here are actually the best visual representation for how AI learns. The type of AI that we're going to be talking about today are called neural networks. Neural networks are behind some of the most powerful AI tech in the world right now, but we're going to be talking about the simplest form of neural networks, densely connected neural networks. So let's start with an abstract representation of a neural network. I put things I know into the box and get out the thing I want. For example, let's say given a car's wind resistance, horsepower, weight, and drivetrain, we want to guess its top speed. So into the box, we put the car's wind resistance, horsepower, weight, and drivetrain. Looks like drivetrain isn't going in. That's because all the inputs to a neural net need to be numbers because the neural network is going to rely on math to work. I know, calm down, I know, don't worry, I'm here. So we have a couple options here. Because we know that there are 4 major drivetrains, we can set front wheel drive to equal 0, rear wheel drive to be 1, 4-wheel drive to be 2, and all-wheel drive to be 3. Okay, so now we have all of our inputs as numbers. What goes on in the box to give us our output? Well, in reality, it's much less of a box and much more of a upside down Christmas tree. Merry Christmas. So to start with, we're going to have 4 nodes at the top for each one of our inputs. You can think of a node like a little circle that holds a number. To start with, these nodes are just going to hold our wind resistance, our horsepower, the drivetrain, remember 0 for front wheel drive, and the weight. You'll notice that these nodes at the top of the net all align horizontally. This is because together they form what's called a layer. Neural nets are composed of layers that feed downward until you get to the output. Let's draw our full neural net. As many middle school teachers have said before me, I am not an artist, okay? So what does it mean for nodes to be connected? What do these lines represent? Well, as data goes into the neural net, we'll start with our input values. When those input values go through a connection, they'll be multiplied by that connection's weight. A weight is just a way for a neural net to keep track of how important values are to other nodes in the neural net. Once this node has all the values above it multiplied by their connection's weight, it'll then summate those values and use that value to multiply by its other connections, and so on. Once we get to this final node here, it'll have the neural net's guess for the top speed. But I left something out. If you're keen, you will have noticed that if this neural net is just a combination of summations and multiplications, it'll only ever be able to model linear functions. So functions that look like that. It would not be able to model functions that look like this, or functions that look like this. So how do we introduce nonlinearity into our neural net? Well, we use something called activation functions. We're still going to multiply these nodes' values by all their connections and then summate that here, but before we pass that value to the next layer, we'll apply an activation function. So let's call our value here, that's the summated value of all these nodes up here multiplied by their connection, we'll call that value z, right? Before we pass z to the next layer, we'll apply an activation function. Let's call that activation function f, right? Common examples of activation functions are the sigmoid function, the hyperbolic tangent, and my personal little sweetheart, the rectified linear unit. I like rectified linear unit because it's the simplest to understand. It takes all positive values and keeps them the same, and then takes any negative values and sets them to 0. So pretty much if the values here is 1, we keep it as 1 and then pass 1 to the next nodes, and if the value here is -1, we change it to 0 and pass 0 to the next nodes. So to summarize, neural nets simply work by taking the input values, multiplying them by the weights of these connections right here, summating them in the nodes below them, applying an activation function, and then using that value to then multiply by the connections weights below it, and so on. And once we read this value in the bottom node right here, it'll have the neural net's guess for where our top speed will be in this example. But all these weights, which are pretty much the neural net's entire intelligence, start out as just random numbers. So how do we get those weights to be numbers that actually give us an accurate top speed? You train the neural net. In order to train the neural net, though, you need a measure of how good it's actually performing. This will be in the form of what's called a loss function. All a loss function does is it takes the predicted outcome, or the right answer, and then looks at what the neural net decided and calculates some measure between those two that will be higher for wronger answers and lower for more correct answers. So what does the neural net actually change to try to minimize that loss function? The weights. Like we said earlier, when a neural net first starts out, it's a collection of a bunch of random numbers as weights, but as it trains, those random numbers will get tuned to the perfect weights to best minimize that loss function. Neural nets can seem really complex, but like we talked about before, they're pretty much just deeply nested functions of multiplication, summation, and our activation functions. And because of that, we can use an algorithm called backpropagation, which relies on the chain rule. And if you remember anything from college calculus, which I don't, you'll remember that the chain rules for deriving nested functions. Backpropagation works by looking at the loss and working backwards to see how each weight affected the loss, and from that, knowing which way to move the weights. Backpropagation is the entirety of how neural nets learn, and while it can seem really mathematical and really complex, I think the easiest way to think about it is you start with that final loss, and then you work backwards to see how each one of the weights in the neural net affected it. Once you finish this, you'll have derivatives for every single weight in the neural net relative to the loss function, which again seems really complex, really mathematical, but I think the easiest way to think about that is just the classic expression y equals mx plus b. The derivative of the weight relative to the loss is just m. It's going to be a measure of how much changing that weight will affect the final loss. A very steep slope will mean that changes in that weight will result in more drastic changes to the loss, where a flatter slope will mean that changing that weight won't affect the loss too much. But in machine learning, these aren't called slopes. These are called gradients. This right here is a gradient. So an easy example to help you understand gradients is to imagine a neural net with just two weights. Imagine that for any given combination of those two weights, you know the loss at that point. To visually represent that, you can imagine these mounds right here, where the x and y coordinates are the weight values, and the height of the mound is the loss at that given point. So when a neural net's first generated, because the weights are random, it's plopped into a random spot in this huge gradient space. And it can't see everything around it, but it can know that in any direction in which it wants to move, how steep the slope is. So if I move in this direction, feels pretty steep, I'll take a step there. Feels like a pretty steep downhill right there, I'll take a step there. That's still steep. It's getting more gradual, but still steep. And I'm at my lowest loss. While the hill example might seem like an oversimplification of backpropagation, I actually think it's the best way to think about it. At any given point, all the neural net's doing is calculating the slopes of each one of its weights relative to the loss and moving downhill to get to that lowest point in the gradient space, or in our example, the hills. Most gradient spaces in real neural net problems are much more complex than the smooth hills that we saw over there, and have many local minimas that the AI can get caught in, or many sharp peaks or jagged edges. But as a simple example, I really like the hills. Most neural nets will also not have two weights. Neural nets now have billions and billions of weights, but it's really not hard for computers to compute gradients, even in those extremely high dimensionality spaces. So to summarize, when an AI is called, data is fed forward through the nodes, multiplied by the weights, and through a combination of that multiplication, summation, and the activation function, the AI is able to predict an answer. And then when it's time to train the AI, instead of going forward, we look backwards and we see how all those weights affected the final loss. Then, through backpropagation, we get those lists of slopes, also known as a gradient, and we travel downwards to the point where loss is the lowest. If you guys enjoyed this video or learned anything, please leave me a like, please subscribe. This is part of a series where I'm posting a video every single day until I get a job in software engineering. I know you're probably watching this video thinking, what, Daniel? You're not a college professor. Trust me, if you guys want to reach out to local colleges, tell them to hire me. That's up to you. But yeah, subscribe. I'd be happy to go over any other thing in AI, how image AI works, how new video creation AI works. It's all stuff I'm super interested in. So let me know, and I'll see you tomorrow.